represent the capital X by this matrix x1 transpose etc. to xn transpose, the whole transpose, and u by this, then the network system can be written in the compact form as x dot t equal to phi x of t plus psi u of t, where phi equal to a plus c cross h. C cross, this cross means the Kronecker product, and psi is the block diagonal matrix d1 b1 d2 b2 etc. dn bn, and a is the block diagonal matrix with the state matrices of each node as the diagonal blocks. This is a representation for a networked system, and I'll now show some interesting examples on the controllability of such a system. Consider a network with two connected nodes with the C12 and C21 equal to 1, and D1 D1 D2 equal to 1 means both the nodes 1 and 2 are under control, and the state matrices are given. State matrices, control matrices, and the observability matrix are given. Here each node is under control, but when we connected it together with this connection C12 and C21 equal to 1, then the whole network, the system is not controllable by the PBH rank criterion. The interesting fact to observe here is that both nodes are under control. Even though both nodes are under control, the whole network system is not under control. One more example. Here also the connection is same, but only one node is under control, and the state matrices are control matrices are given. Here each components are observable. Even though each component are observable, the whole system is not under control. And one more example. Here also the connection is same. There is a connection going from the node 1 to 2, and a connection from 2 to 1 is also there, and only one node is under control. The control matrix, state matrix, control matrix, etc. are given. Here AB is not controllable. Then even then the whole network system is controllable. So you have observed that even though only one node is under control, the whole system can be controllable. So these are the things that we deal with the controllability of a networked control system. So I'll now move to my model under consideration. Here I am considering each node is observable with the is in the node dynamics given by this equation. Xi is the state vector, Wi is the input vector, Yi is the output vector, and Ai is an n by n matrix, which is the state matrix. Bi is the n by n column vector, which is the control matrix, and the dynamics of the system is given by these matrices Ai, Ba, and Ci. And composing these n nodes, we can construct a network, the global system sigma n, which is of global system with sigma n, where the input vector Wi of t is given as a linear combination of the output vector and the control vector, and it is given by this, where gamma ij represents the connection strength between the link from the node Vj to node Vi, and delta IL is the connection between the control node UL to the state node Vi, and both become 0 when there is no edge in the network graph between the state nodes and the control nodes. And by composing these values of gamma ij and delta ij, we can construct these matrices capital gamma and capital delta. Then the system can be converted to the compact form as fxt plus gu of t, where f is given by this matrix, which is of dimension capital Nn by Nn, and g is of the form this form of dimension Nn by M. And in this work, we'll be studying the controllability of the global system sigma n in terms of the component matrices Ai, Bi, Ci. The interesting fact here is that we are checking a way of structural controllability of the system. Means we in real life applications, we may not be able to find the parameters of the component matrices always. So structural controllability means for some numerical, we will get some parameter matrices as the components, and we will check the controllability as if it is controllable for some numerical realization, then we will say that the system is controllable. So here the matrices gamma and delta are in the parametric form. Ai, Ba, Ci are we know the exact values of the members. So here we will be checking the controllability of system where the matrices gamma and delta are in parametric form. One result was published in recently 2020 June by Christian Comalt and Alan Kibango for the homogeneous systems, in which a set of necessary and sufficient conditions were given for the generic controllability of a system with the homogeneous dynamics. We were able to find a counterexample for that. Even if the set of conditions are satisfied, the set may not, the network system may not be generic controllable. So we will be we find some necessary and sufficient conditions, for the generic controllability of a networked system with the heterogeneous dynamics. The first theorem is this: if the pair AIBA is not controllable for some I, then the global system is not generic controllable. So for the system to be it is a necessary condition. So we are giving an example here. The nodes are having different dynamics. A1 is given by this matrix, A2 is given by this matrix, and the control matrices are the same, and the output matrices are also the same, and the connection network topology matrix and the delta matrix are given by this, which are of the parametric form. And we can calculate F as we have seen earlier, and here A1 B1 is controllable, but A2 B2 is not controllable. Then by our theorem, the whole system is not controllable. We can verify this by the PBH criteria, as the matrix F minus I G has at rank at most 3. The whole system is not controllable. And another result we get is that if the number of nodes is greater than the number of control inputs, the global control for the global system to be generic controllable, at least one of the pairs AICI must be observable. At least one of the AICI must be observable. We are giving an example for this. Consider a system where the nodes A1 and A2 are given by this, and B1, B2, the output matrices are given, and the parameter and the connectivity network topology matrix gamma and delta are given. We can calculate the matrices F and G like this. Here both A1 B1 and A2 B2 are controllable, but A1 C1 and A2 C2 are not observable. Also n greater than m. By the above theorem, by our result, the whole system should not be controllable. So by previous,
you have 1 minute left.
Okay, sir. By PBH criterion, we can verify this. As this matrix has at rank at most 3, the system is not controllable. And another one result is, if the graph G of n is not control connected, then the global system is not generic controllable. So it should be the graph should be control connected. That means there must be at least one connection from the control nodes. So here I am giving an example. A1, A2 are given. A1, the parameter is given here. It is easily seen that the graph is not control connected, as only gamma 1, 2 is there. Sorry, as only delta 1, 1 is there. And the graph G of n is not control connected, and the matrices F and G we can calculate as F and G, and by the PBH criteria we can verify that this matrix has rank at most 3 only. Therefore, the system is not generically controllable. And these are the references that some important references that I used for my work. Thank you.
Please ask some questions if you have from audience.
So you have somewhere you have shown some polynomial matrix, and you have written a maximum rank of that matrix. So I would like to know that
not polynomial. The parameter value we don't know exactly.
Okay. Yes. So the parameter value we don't know. So how do you calculate that its rank is maximum of something?
Okay. How this matrix has rank at most rank 3 only.
Yes.
Here the fourth row is completely 0, sir. So it can have only a rank at most 3.
Okay. So here the structure is very simple, but it is possible that for some other matrices, when there are parameter included, the structure is quite complicated. So that we cannot can we, in that case also, do we have any method where we can conclude the at most rank of some parameter matrix?
It is very it will be difficult, sir. I don't know if any such methods exist there.
Okay.
I'm not aware.
Anybody else? I have a question.
Yes, sir.
You have defined a term generic controllable
Generic
global
controllability.
system.
Ah.
So can you give one example of generic controllable global system?
Generic controllable global system. Sir, I have to write it. Okay. Sir, generic controllable, the idea is for some numerical realization, it should be controllable. It must have a rank, full rank, this matrix.
You have considered some examples which are not.
Yeah.
Yeah, so I am asking whether you have any example which in support of that.
For the system is controllable. Generically controllable. Sir, I have,
Yeah.
but not, I have to write it.
Okay, it's okay. So, okay, thank you very much.
Okay, sir, thank you.
Now, next presenter.
Yes, paper ID 26. The title of the presentation is
Yes, sir.
Yeah, M. HYMAVATHI. Yeah.
Yes, sir. Yes, sir.
Yeah. Please share your screen and start your presentation.
Okay, thank you, sir. Is it visible, sir?
Yes.
Yeah.
Okay, sir. Shall I? Now, can I start, sir?
Sure, you start.
Yeah, okay, sir. My name is M. HYMAVATHI, sir. I'm PhD scholar under the supervision of Dr. M. Syed Ali, sir. MSc MPhil PhD. Assistant Professor, Department of Mathematics, Thiruvalluvar University, which is near to Vellore. Actually, my topic is synchronization of fractional order neural networks with time varying delays via pinning control. My plan of presentation: abstract introduction, fractional order calculus definitions and system description, main results, numerical example, conclusion and references. Abstract. Actually, my paper, it will show that the synchronization of fractional order neural networks with time varying delays via pinning control are investigated. Firstly, some sufficient conditions are derived for assuring the global asymptotical stability of the system. I have to apply here Lyapunov function and some inequality techniques. And also I have to use here a Kapto fractional derivatives. Further, a numerical example is given to verify the validity of the feasibility results. And introduction. What is fractional calculus? Many of them, they have a doubt what is meant by fractional order calculus. Here, it is, when we comparing to the ordinary differential equations, it is easy to find out the half derivative and complex and real numbers. When we compare the ordinary differential equations, which is not find out like half derivative like that. So when we in fractional differential equation, it is easily find out. And here its origin go back more to the year of 1695, the conversation of El Hospital and Leibniz. So here dear hospital, he will get it out. What is n equals to 1 by 2? So Leibniz, it will be lead to a paradox from which is one day useful consequences will be drawn. So here we are using in the fractional differential equation, we are using some definitions like Riemann-Livoli and Granville-Capito and Miller-Ross, etc. Now we are discussing about the neural networks. Networks science is generally a young research field. Network is a set of items which we call as vertices are here, and there is a nodes with association between them called as edges, represented in the presence of the connection or interconnection among these components. Here, if you wanted to observe in figure, you can easily identify it. Here, each and every node should be connected with one edge. Each and every edge should be connected. So this is said to be one of the example of neural network. Now these are some definitions of neural networks. And then here we have to draw how to draw a system. We can easily identify here. Here x1, x2 up to 7, xn are set to the inputs, and w1, w2, w3 up to 7, wn are weights. And if you wanted to summing into a junction, we will get here f is set to having an activation function, and we will get like v as set to be output. Recently, many research have been introduced the fractional order neural networks. So now we have to discuss about synchronization. The starting point of the word synchronization is a Greek root. So the historical backdrop of synchronization results to be a 17th century Jews, the celebrated with Dutch researcher Christian Huygens have an account his perception of synchronization of two pendulum clocks. So obviously, a time delay inherited occur in the real applications of neurons, especially at synaptic levels due to the finite conduction speed of the amplifier or hardware implementations of neural networks in the process information transmission between two neurons. And so if it is a synchronization system, you can easily identify that subsequently the response system is balanced to a slave system. The best of possible functions of dynamics of the drive system, which goes about the external, however, chaotic forcing of the response system. Below shows that the basic model of the master and slave system of the nonlinear system, which through an appropriate controller. So, if you observe in the diagram, master system is there and slave system is there. If you wanted to subtract both, we will get error system, that is, and we can add it into a controller into that. So, the figure it will show us like this. And now we are going to discuss some time delays. A time delay is an important issue of studying the fractional order differential equations, because it is not only discrete time delays, but it is also described the distributed delays also. It's a major role in the research, the synchronization of problems. Time delays are exhibited in numerous physical procedures because of the time period. In addition, a long period has associated its events. Now we have to discuss about the Lyapunov stability theory. The Russian mathematical Lyapunov methods determining the stability of systems. The first is the linearization method, where the linear stability of nonlinear system is found by analyzing the stability of linear model that is obtained by the linearization of nonlinear system of the neighborhood of. This method is able to analyze only a local stability of the nonlinear system. The second method is known as the direct method of great generality, because it doesn't involve the knowledge of the solution.
രജിസ്റ്റർ ചെയ്തില്ലെങ്കിലും ആധാർ കാർഡും കൊണ്ട് അവിടെ ചെന്ന പേരൻസ് ചെന്ന മരുന്ന് തരുന്നു.
Abhijit, please mute yourself.
Now we have discussed about the system description. In this paper, we are concerned with the following fractional order neural networks with time delays as a master system, which can be expressed as. So master system can be explained like this. So d power beta is said to be a capital derivative of order. Then beta is lies between 0 to 1. And p of t denotes the neural states, and rj, which is greater than, denote the self-feedback connection weights matrices. So here djk and sjk are respectively. connection matrices only. So JJ ensures external bias. So here GK, PK of T and FK are said to be the activation functions. Now the slave system can be represented here. And if you wanted to here, if you subtract error master system and slave system, we will got the error system that can be represented here. So before going to error system, we had to introduce here pinning controllers. That is Wj of t equals to minus kj mu Uj of t. Here j is ranges from 1 to L, and Wj of t equals to 0. Then j is ranges from L plus 1 to capital L. So here kj and j equals to 1 to L are positive constants. Now we have here error system like this. And here, if you wanted to find out the fractional derivative, we can use some definitions that are capital fraction derivative of order beta function f of t is defined by like this. So d power beta of f of t equals to 1 by gamma of n minus beta. So integral b to t minus tau power of n power b minus 1 f power n of tau into e2. So here I am using here the lemma like this, and then lemma 2. Here if it satisfies, so my actually, okay, then the lemma it satisfies means my theorem should be satisfied. So here I am using the assumption like this. So first of all, the first theorem is suppose that the assumption 1 and lemma 2 it hold, then the theorem 4.4 is globally asymptotically stable. So let us consider the Lyapunov function here, that is v of t equals to 1 by 2 u for u transpose of t u of t. And here by using the lemma 1, if you wanted to apply the capital derivative in the above function, in the Lyapunov function, then we will got like this. Then if you wanted to take a capital derivative, then we got by applying lemma 1, we got like this. Then we will substitute into that values into the error system. Then we will got like that. And by using some simplifications, we got like this. And then by using the Lipschitz condition, we have to write like this. And so finally, we got the solution like this. So here lambda, which is greater than root 2 into summation nk, the system 4.2 is a global asymptotically stable. So here lemma 2 we can observe that lambda, which is greater than root 2 into summation nk. So we can say that limit n tends to infinity modulus of xa equals to 0. So that is, we have to say that by the definition of the global asymptotically stable. So that's here we have to say that if it satisfies like this, means I have to say it should be a global asymptotically stable. Now it is convenient to write like this. And here I have the same error system. In the second theorem, I have to use the same error system only, but I can use here some adaptive laws. Here d power beta of c, d power beta c of t equals to b beta into summation j equals to 1 to n phi uj square of t. Now I have to use here the Lyapunov function like this, and I can use the capital derivative here. And if I have to use the capital derivative by using a lemma 1, you can directly substitute the error system like this. And some simplification finally will got like beta k. So finally we have to say that if it's satisfied like this condition, means we can say the system is a global asymptotically stable. Then I have to discuss about the numerical examples here. Let us consider to take the master system like this, and here j and k, it will take the extents value from 1, 2, and here I have to choose the values beta and r1, r2, like these values I have to choose with the activation functions fj of pj and also fj of qj and gj of pj and gj of qj. So from that, if I have to substitute these values into this function, then we will got like this. And here lambda value, which is lambda equals to 24.3, which is less than neta value. So we can say that the system should be satisfied. It satisfies the global asymptotically stable. Here conclusions. Here we researched the synchronization of fractional neural networks, the delay by pinning control. So here I have to use some inequalities, and also I have to use the Lyapunov functions, some inequalities to derive the stability conditions by using the master and slave system of the synchronization. Finally, a numerical example is demonstrated. So here are some of the references. Okay, thank you, sir. Hello, sir.
Yes, some questions from audience.
Okay, sir.
Okay, I have a question. HYMAVATHI, can you please go to slide number 19?
Okay, sir.
Yeah, just the definition. I wanted to know, here n takes the value from natural number set. So what will be the case when beta is equal to n?
I didn't understand your question. Can you please tell me loudly, sir?
Yeah, I'm repeating. I wanted to know, it is the definition of the capital left fractional derivative. I
Okay,
wanted
sir.
to know if we take beta equal to n, natural number n, small n. So what will be that?
I didn't hear, sir, properly.
Yeah, I wanted. I was asking it in different fashion. So can you tell, if we take the limiting case for natural numbers, so
Okay,
what,
sir.
how the capital derivative will be? Is it convert to the ordinary normal standard derivatives or no?
I think it is possible, sir.
Okay.
By using the Fourier transformation, we can solve it, sir.
Okay. Another question is, can you you have mentioned in the introduction that apart from capital we have Riemann-Liouville fractional derivative. Okay.
Yes, sir. Yes, sir.
Yeah. Can you tell at least one difference between them?
I didn't understand, sir. Will you please tell me again, sir?
Yeah, I'm asking that, do you know the difference of capital fractional derivative and Riemann-Liouville?
Yes, sir. Yes, sir.
Yeah. What is it? Tell any difference.
Here,
Hello.
here we are using the capital derivative initial conditions. If you know the initial condition, we can use the capital derivative, sir.
Okay, from my side it is okay. Any others can ask question.
It's okay. You may leave now. If no, thank you.
Okay, sir. Thank you, sir. Any question?
Okay, next.
I think you go in the math.
The next presenter, Praveen, P27. Are you
Yes,
there?
sir. Yes, yes sir.
Okay, so you may share your screen and start.
Okay, sir. Okay. I share this. Yes, sir. My slide is visible.
No, it's not visible. Yeah, now it's visible.
Okay, sir. Good afternoon, sir. And myself is Parveen Kumar. I'm PhD research scholar, NIT Hamirpur, and I present my presentation and title is Approximate Controllability of Non-Autonomous Second-Order System with Infinite Delay. Next new just yes. These are the outlines of my presentations: abstract, introduction, preliminary, assumptions, result, and references. The abstract in this paper, we find the existence in approximate controllability for the second order non-autonomous systems with infinite delay, and the approximate to stability is the sufficient condition for the proposed control problem. The theory of evolution operator and Schroeder fixed point theorems techniques are used. And introductions, in introductions we gave the definitions of controllability. Controllability means to check the existence of forcing term and control functions ut such that the corresponding solutions of the system will passing through a desired point. And the definition of approximate controllability means that the system can steering from an arbitrary initial state to an arbitrary small neighborhood of a final state. And next is the preliminaries. And before prove the main result, we give some preliminaries which are used in our result. And the definitions of evolution operator. Evolution operator is a bounded linear operator. Is defined in the form of in having the some assumptions, some conditions. These conditions is D1 conditions, and in which first psi of t comma t equal to 0, and second is for all t comma s belong to the interval 0 to t, and for each x belong to the Banach space x, having the partial derivative with respect to t is equal to x, and the partial derivative with respect to s is equal to minus x. And another is assumptions is D2, and and D3 is another assumptions on the evolution operators. And next, the definitions of strongly continuous cosine family. A one parameter family of boundary linear operator map the Banach space X into itself is called strongly continuous cosine family if and only if it satisfies the conditions of cosine family and it is continuous for all t on R and for each fixed point X in the Banach space X. And next, the definitions of phase space. And phase space, the linear space of functions and map minus infinity to 0 to a Banach space X and having the semi-norm, and verify the following axioms in B1 axioms and B2 axioms. And in these assumptions, we assume that the cosine family and cosine family is bounded by the constant and n tilde. And now we define the mild solution of the problem phi. The mild solution of problem phi is defined on the form of integral equations of 1, and a function is approximate. The system phi is called approximate controllable if the reachable set is dense in a Banach space X. And for the controllability of the problems, we define the operators and controllable operator and resolvent operator in the form of equation number 2 and 3. And the hypothesis as is that if the resolvent operator approaches to 0 as alpha tending to 0, then the system is given in the form of 4 is approximate controllable. And now to establish the controllability result, we require some assumptions. First, A1 is the evolutions operator is compact operators. The functions have satisfy the following conditions. F is strongly measurable functions, F is continuous function, and F, a function defined from J cross space P to X, is continuous and uniformly bounded functions. And A4 assumption is that rho is a continuous and the function T to psi t is well defined and condition from V of rho inverse 2 is this. And next is a lemma which are used in our result, and to prove the result we introduce the following notations. And the norm of a bounded linear operator C is equal to MC, and K is a constant which is equal to x of t, and h t and t, and phi norm or phase space P and K star is given in this form. And we consider the second order differential equations with non-autonomous system is of the form of equation number 5. And where work kappa is a state function in a Banach space X, and F is a function from J cross space P to a Banach space X, and U is a control function in a Hilbert space U, and P is a phase space, and the closed linear operator is generate a continuous cosine family phi t, and the operator C is a bounded linear operator from a Hilbert space to X. And x of t theta is equal to x of t plus theta for theta belong to minus infinity comma 0. And the result is the system phi has a solution on the interval J if the assumptions A1 to A5 are satisfied for all alpha greater than 0, and it satisfies the equation number 6. Before solving the problem, we take a space Z of the space of all continuous functions having the conditions x of 0 is equal to phi 0 and with uniform norm, and Z in space Z we consider a subset Q in which x work kappa is the from a Z having the norm less than equal to R. To prove that our result, we use the following step. First step, we define a operator f alpha from the Z to Z, from the set Z to Z is given in the form of f of alpha xt is equal to phi of t comma 0 phi 0 and psi of t comma 0 xj 0 integral 0 to t psi of t comma s c of us plus f of st work kappa rho t comma xt and ds. And in second step, we show that this map is a self map. It means, and we show that f of alpha q is the subset of q. And next, in third step, we prove that we show that for each alpha, the operator f of alpha map bounded set q into the relatively compact subset of q. And in fourth step, next we will show that f of alpha is a continuous map. And in fourth step, by using the sort of fixed point theorems, and we say that these systems have a fixed point, and this fixed point is the solutions of our systems. And next result is assume the linear system corresponding to phi is approximate controllable on the interval J. If the assumption A1 to A5 are satisfied, the system phi is approximate controllable. With the help of result 1, it says that the system has a fixed point. So with the help of this, we assume that the system phi has a fixed point and x alpha be a fixed point of f of alpha in Q, and define a control function u of alpha t is equal to c star psi star and t of t and r alpha resolvent operator r alpha 0 to t and p of x alpha, where p of x alpha is defined in the equation number 5. And we use the following step. And first step is, in first step we prove that norm of f p of x alpha minus w norm approaches to 0 as alpha tending to 0, where w is given in where w is a function written in the form x of t minus phi of t comma 0 psi 0 and minus psi of t comma 0 y 0 in minus integral 0 to t psi of t comma as f of s and x rho t comma xt ds. In second step, and we get the norm of x alpha t minus x of t norm less than is equal to the norm of resolvent operator plus norm of p of x alpha minus w norm. And in third step, we get x of alpha t minus x of t norm approaches to 0. So with the help of these three steps, we see that the system is approximate controllable. Thank you, sir. These are the references of my related to my research work.
Questions from audience?
So Praveen, I want to make one suggestion to you that
yes, sir.
You don't need to speak every part of a mathematical expression.
Okay, sir.
Okay, so you can give them equation numbers, and then you can refer equation numbers that the condition 2 is satisfied. It is given by following condition 4, like that. So like you have spoken each and every part of that.
Thank you, sir. Thank you. Okay, sir.
Okay.
Can you give one example of phase space 3?
The one example of phase space 3 is L2 0 comma t. The Lebesgue space L2 0 comma t on space. L2 space is the phase space examples on the interval 0 to 0 comma t.
Okay, you may leave now. Thank you.
Sir. Thank you, sir. Thank you so much.
Next presenter, Ankit.
Yes, sir. Sir, is my screen visible, sir?
Yes, you may continue.
And am I audible, sir?
Yes.
Clearly? Okay. First of all, thanks to provide this opportunity. I am Ankit Kumar, research scholar in the Department of Mathematics and Scientific Computing, NIT Hamirpur, under the guidance of Dr. Ramesh Kumar Vats. The title of my presentation is Approximate Controllability of Fractional Sobolev-Type Differential Systems. These are the outlines of my presentations: introduction, preliminaries and assumptions, results, example, conclusion, and then references. In this work, we consider the following Hilbert fractional differential equations of Sobolev-Type with a non-local initial condition in a Hilbert space. Controllability is a fundamental concept of mathematical control theory introduced by Riemann R. Kalman in 1960, which means if we can steer our dynamical system from any initial state to any arbitrary final state with the help of some functions known as control functions, then we can say that our system is controllable. In this work, we use the Hilbert fractional derivative d sigma nu of order 0 between 0 and 1 and type of nu between 0 and 1 on the interval 0 to t. Here, the R, A, and B are the linear operators in this problem, and this is the Riemann integral operator. And in this problem, we consider as non-local initial condition as well. Non-local initial condition means we consider a function rather than a single point. Preliminaries and assumptions. Let H be the Hilbert space with inner product, and also we define another space H tilde with the supremum norm. The Riemann fractional integral operator is defined in equation second. Hilbert fractional differential operator is defined in equation third. Hilbert fractional derivative is basically generalization of Riemann fractional differential operator as well as the interpolation between Riemann and Capito fractional derivatives. Then we consider a Cauchy problem in equation 4. In the infinite dimensional case, if we go through the solution of our main system, then we go approach to some operator families. So in this work, I have considered a family of bounded linear operator parameters P of t, and which is exponentially bounded and having the condition both are given in equation 5 and 6. And also we consider some conditions P1, P2, P3. This is the mild solution of our main system defined in equation 7. Lemma. The operator family P alpha is non-continuous, and the associated families with the operator family P of t are Q sigma and K sigma and S nu sigma, and they are also bounded by some finite quantity given in equation 8. And then we define the controllability operator in equation 9 and resolvent operator in equation 10. B star and K star are the adjoint operators of the operator B and K respectively. In this work, to show the existence of the mild solution of the system, we use Krasnodar fixed point theorem, which states that if S is a closed, bounded and convex subset of Banach space H, let F1 and F2 be two mappings such that F1 x1 plus F2 x2 belonging to S. For each pair x1 x2 belonging to S. If F1 is contraction and F2 is completely continuous, then the operator equation F1x plus F2x is equals to X has a solution on the set S. In order to establish our results, we required some hypotheses that are given as A1 and A2. Now we define the control function in equation 11. And for the sake of convenience, we introduce some notations defined in equation 12 and 13. And we define two sets in equation 14, which will help to useful for our further actions. Result 1. Assume that the hypothesis A1 and A2 are hold, then the control system corresponding to the control function defined earlier has a mild solution, provided that the inequality given in equation 15 is hold. Due to the time constraint and the lengthy proof, we just show here the steps which I have followed to prove this result. First, we define the control function. And with the help of control function, first we define an operator f alpha in equation 16. We define this operator in such a way that the fixed point of this operator will become the solution of the main system. So next, we define another operator associated with the operator defined in equation 16 in equation 17 and decompose this operator f alpha in two parts, f alpha 1 and f alpha 2, defined in equation 18 and 19 to apply the Krasnodelsky fixed point theorem to show the existence of the system. And then we show that the f alpha operator f alpha 1 is contraction and the operator f alpha 2 is completely continuous, and then apply the Krasnodelsky fixed point theorem to complete the proof. In result second, if the hypothesis a0 to a2 hold and the function f and h are uniformly bounded, then the Hilbert fractional differential system 1 of Sobolev-Type is approximately controllable. To show the to illustrate our main results, we consider an example as well in equation 20, and these are, now we define the operators a and r in equation 21 and 22, and the operator family p of t in 24, and we can see that this family is generated by the operator pair of a r inverse and bounded by 1. Conclusion. In the presented work, we established the sufficient conditions for the approximate controllability of fractional Sobolev-Type differential system in a Hilbert space. In the proposed control problem, we use the Hilbert fractional derivative, which is an interpolation between Riemann-Leibel and Caputo fractional derivative, as well as generalization of Riemann-Leibel fractional differential operator. And also we consider in this problem non-local initial conditions. In many cases, non-local initial conditions are more appropriate and have better effects in applications than the classical ones. The main tools used in this analysis are resolvent operator, semigroup theory combined with the Krasnodelsky fixed point technique. And at the end, we provide an example to illustrate our abstract results. These are the references. Thank you.
Some questions from audience.
So I would like to know that what is the meaning of approximate controllability for any normal control system.
Will you repeat, sir, your question, please? I can't hear properly.
So that is a word. You have used a word approximate controllability.
Yes, sir. Yes, sir.
So I would like to know that what is the definition of approximate controllability for a normal control system, for a general control system, for example, x dot equal to ax plus b.
Okay, sir. Approximate controllability means if we can steer our dynamical system from any initial state to any arbitrary final state. Okay, sir. In finite dimensional case, both exact controllability and approximate controllability are the same. Approximate controllability has no meaning in finite dimensional case. It is meaningful in infinite dimensional case. Yes, sir.
So is it the same for non-local initial conditions? Does it have any meaning for finite dimensional case?
Yes, sir. In non-local initial conditions means we consider a function rather than a single point.
Okay, so again the same thing. It doesn't mean in anything in infinite dimensional space, right?
Yes, sir.
Okay. Thank you.
Thank you, sir. May I leave, sir?
Yeah. You have used Hilbert fractional differential operator.
Yes, sir.
So, is there any more such differential operators? How you decided to apply this in your work? Is there any method to choose better?
Yes, sir. Before I using Hilbert fractional derivative, I work on with the Caputo fractional derivative. But in Hilbert fractional derivative, when here is the type of sir, here is the type of nu of the, this is the two parameter derivative also. So if we nu is equal to 1, then in case of v equal to 1, it becomes capital fractional derivative. And if it the type of nu is equal to 0, then it behaves like a Riemann fractional derivative. So basically it is generalization of Riemann fractional derivative and interpolation of between Riemann and Capito. So that's why we use this fractional derivative in this work.
Okay, so Kapil Kumar raised his hand, so
Yes, sir.
you may ask your question. Is this question related to his presentation? Okay, so thank you. You may leave now.
Thank you, sir. Thank you very much.
The next presentation is from V. Gokul. Are you here? P29. So
I think sir, he is not here.
yeah.
No. Actually,
So we may call for the next presenter. Dr. Kundu.
they are the major expert of.
Yeah, sir.
Yeah, what we should do? We can call for the next presenter.
Yes, we should call the next. Then we will wait for some time for that one. Okay.
Yeah, P31, Sumit. Are you there?
Yes, sir, I am there.
So you share your screen and start your presentation.
Yes, sir. Is it visible?
Not. Yeah, now it's visible.
So, may I start now?
Yeah.
Thank you so much, sir. So myself, Dr. Sumit Kumar Pandey. Currently, I am a faculty in the Department of Electrical Engineering, IST Shibpur. And here I will go to present a work on that 2DOF, 2 degree of freedom, PID control design for control of NEMO system. So before going to our work that I want to present, I just want to introduce that first, what is 2DOF, what is PID controller, and the control of NEMO system. Actually, generally, the NEMO system is termed as a multi-input, multi-output system. And when a system having number of inputs more than one or number of outputs more than one, then it is the case of a multi-input, multi-output system. That can be furtherly classified in a different way. That is, whether it is a square NEMO system and the non-square NEMO system. In the square NEMO system, the number of input and output will always be same. Whereas in case of a non-square NEMO system, the number of input and output is different. In the case of a non-square, the control of the non-square NEMO system is again a tedious task as compared to the square NEMO system. Although the control of a NEMO system is also a complex task for getting the desired response. And why I am telling that it is a complex task, because in case of a multi-input, multi-output system, that is the NEMO system, there is a coupling effect that is present in the NEMO system. The coupling effect means when I want to control the first output, if I am considering, just we consider one example, that 2x2 NEMO system. It means there is a 2 input and the 2 output. So if I want to control first output with respect to the first
I
input,
think you should choose the view from view option, full screen mode. From view option.
I will do it, sir.
Yeah, then.
Is it now?
No. View option is there.
I have converted it to full screen. It is not visible.
No, it's not visible.
Okay, okay, sir. Wait a minute, sir. Just wait a minute.
Yeah.
I just go to the and
No,
just
your
sharing my
screen is
screen.
visible, but it is not in a maximum mode. So there are some
Okay,
other
okay. No,
things
but I have
which are
no,
not
no. I
needed.
have no, no. I
Your
have done
audio
it, but
and pictures are not matching.
no, no, sir. Right now, I am not increasing my slide. That's why it may not be visible. I hope now it will be visible.
Yeah, now it's in full screen mode.
Okay. So that I am telling that the MIMO system difficulty. Yeah. Now one of the common example of the MIMO system is the TRMS, that is known as the twin rotor multi-input multi-output system. This is the diagram of the twin rotor multi-input multi-output system. This is the laboratory setup of a actual helicopter system. Like in the actual helicopter, there is a two fans. One is known as your main rotor and another one is your tail rotor. The main rotor, that is that rotor having big in size, is termed as the main rotor, and it is responsible for the pitch motion, means the motion in the vertical direction, whereas this tail rotor is the responsible for the motion in the yaw direction. It means there is an x-axis direction. So we have to control both pitch axis as well as yaw axis. It means the vertical movement as well as the horizontal movement at the same time. And here in this twin rotor MIMO system, there is an effect of coupling occurs. It means that when we control the pitch angle, that is the main rotor, then at the same time this main rotor also affect on the performance of the tail rotor. So it causes the coupling effect on the tail rotor. That's why the control of this TRMS plant is quite difficult as compared to the normal MIMO system, because there is a strong coupling effect present on this. For this coupling effect, for this TRMS, we have considered the laboratory setup of that is provided by the feedback instruments. And for this setup, when we go for the linearization of the mathematical modeling of this complete TRMS, where we have considered all the forces that are acting on the vertical as well as on the horizontal axis, and we linearize across an equilibrium point, because we have designed the controller for the linearized plant, whereas the real system is a non-linear type. So first we have to take the mathematical modeling, then we have linearized it, and we will get a transfer function in this form that is written as GS. This is the transfer matrix of twin rotor MIMO system, that is known as TRMS. Here, this transfer function, that is 1.246 upon s cube plus 0.9215 s square plus 4.77 s plus 3.918. This is the main rotor transfer function, means for first input and first output for this transfer function. Now this G22, that is 3.6 upon s cube plus 6s square plus 5s, it is the transfer function for the tail rotor. This is the tail. So our objective is to control this main rotor as well as tail rotor. So we will take the plant as the main rotor plant for this and the tail rotor plant for this. And this is this transfer function, that is G21s, that is also known as 1.482s plus 0.4234 upon s to the power 4 plus 6.33. This is the coupling effect, that is the G21, means the output of the second is affected due to the input on the first, means the output of this tail rotor will affected due to the motion of this main rotor. That is the coupling effect that is present in this TRMS. So for this, we have to design the controller in this form. This is the conventional control scheme where the reference has been given, and for main and tail rotor we require two controllers, and there is a 2 DOF controller, that is the 2 degree of freedom controller has been implemented. The control scheme of this 2 degree of freedom controller is shown here. So here that 2 degree of freedom controller, there is HS by Fs and Qs by Fs. Now this feedback HS by Fs transfer function is responsible for the providing the stability of the system, whereas this Qs by Fs transfer function is responsible for improving the transient performance of the system. Although we can implement without the 2 DOF freedom controller, that is a single freedom controller. But here, if we are using the 2 DOF freedom controller, we see that the transient performance of the system is quite improved. So this is the transfer function of this HS by Fs, where we have to implement this. Now, the objective is to that this HS by Fs is the PID controller transfer function. So what is first PID controller? The PID controller where we have the Kp, Ki and Kd values. Now the values of this PID controller, that Kp, Ki and Kd value, is obtained through a specific theorem that is known as the Kritanov Theorem. And this Kritanov Theorem is responsible for the robust stability performance of the system. So for this Kritanov, if the polynomial that has been the characteristic equation, that we can say that the characteristic equation, if we term the characteristic equation in terms of this 4 interval polynomials, and if this 4 interval polynomials satisfy the Routh-Harwich stability criteria, then we can say that whole range of this x0, y0 means the lower and upper range of this system will be stable. So if we are taking the Kp, Ki and Kd values and the lower and upper range has been obtained, and if satisfies this condition, then this we can say that the whole range of the PID controller is stable. So to obtain this following this procedure, we will get the Kp, Ki and Kd values for the main as well as the tail rotor, as written here, that Kp for the main rotor is 0.1, 2.5, Ki is 1 to 10 and Kd is 0.5 to 0.9. Whereas for the tail rotor, it is 2.5 to 10 to 1 to 1.5 and 0.16 to 5.5. Now, again, from this range of the values, our other objective is to find the optimum value, that for which value the system will show the best performance. And this has been obtained by the sensitivity characteristic of the system. So we plot the sensitivity characteristic for both main rotor as well as the tail rotor. And this sensitivity characteristic, that the peak value is not greater than this 2 and the transient value is approaching towards the 1 value. That is the criteria for the sensitivity for the system is completely robust. So it can be seen from this both the figure that the system performance shows the robust characteristic. Now, in the real time, with these values of PID controller, we have implemented in the simulation as well as the real time results, that is the experimental result that has been shown here. And it can be said that the system is stable. So we can see, so this is the result of this TRMS system for the main rotor, and this is the control signal. And there is a limitation in the twin rotor MIMO system that the control signal will not go beyond the 2.5 volt. Therefore, we can see that this result will show the satisfactory performance. Whereas for the tail rotor also, it is not go beyond the 2.5 volt plus minus 2.5 volt. And the transient performance is also quite good as compared to the literature work that is available in the literature. So we can say that the system is shows the satisfactory performance. So we can say here that here I can design a successfully 2D PID controller for the control of this twin rotor MIMO system, and it has been successfully validated through the simulation results also, the theoretical parts. Thank you so much, sir.
Questions from audience? Okay, so I want to know one thing here. In TRMS model, how you have decided modeling your system matrix A?
Sir, actually, in our work, in my work, we have not focusing on the modeling part. We have just taken the modeling part from the literature available, and we are our aim is to design the controller. Although the A part has been obtained from that non-linear equations, that is the acting forces on the mean and tail rotor, where we have considered the gravitational force, the gyroscopic moment, the frictional force, every force that has been considered. Through this force, we obtain the nonlinear equations, and this nonlinear equations has been converted to obtain this ABCD matrix, and this parameters has been given in the feedback instruments, that manual of this twin rotor memo system, and we are strictly following the manual of this feedback instruments.
Okay, actually you have not cited there how.
No, I have cited
from where.
Okay, okay, sir.
Okay. It should be. Is it there?
Yeah. The citation is not. I hope that it is not. I have not written, but this manual I have cited.
Yeah, actually, I was interesting to know how the size of this matrix A was decided.
Sir, actually,
based on the factors.
They're based on the factors. If you go, there will be 7x7 matrix. There will be some paper where they have considered the 6x6. It means that they have neglected the coupling effect that is present in the plant. So, if we consider all the effects that have been present in the plant, then this size of matrix of A is depending.
So, is your work is published somewhere?
Yes, sir.
Okay.
So I have one question. Is there any advantage or drawback of PID controller compared with only proportional controller?
So advantage is there that when we are going for the integration part, then the steady state error is completely removed in case of a PID controller, but it is not possible in case of a P controller. But if the plant has already an integrator, then we can go for the P controller. There is no need to go for the PID controller.
Because differentiation is involved here, so it may occur some noise in the data. Is that so?
Sir, yes, it may. Yeah, it may occur some noise on the data. Yeah. And
because
sometimes also I have also do in this direction that we can use the derivative filter coefficient in this case, and by using of this derivative filter coefficient, this noise has been removed. That I have also done, and I have seen that in the real time also.
Okay, thank you.
Okay, thank you. You may leave now.
Thank you, sir.
We have one presentation left out. P. Gokula Krishnan. Are you there? Paper ID P29.
So whether we should stop this session or?
I think, yeah, the part that is there any